So welcome. This is the session where we will be studying further in terms of the discrete time Fourier transform. I hope you have been able to read the corresponding portions from Oppenheim and Schaefer and from other reference books, and you have started to gain a good understanding of what the discrete time Fourier transform is and some of the useful properties. What we will do today is to develop it further, look at some of the properties, look at some of the applications. So again, today should be an interesting class where we will get new insights into the understanding of the applications of the discrete time Fourier transform. As always, we will begin with a quick summary of what we have reviewed in the last session and add some insights to it. So basically, it will not just be a review, but some new insights as well. So the topic that we are covering now is discrete time Fourier transform. It is found in chapter 2, sections 7, 8 and 9. We have already covered the section 7 and 8, and today we will be covering section 9. So basically we will, that's what we will be looking at. So to complete the discussion, so we defined the discrete time Fourier transform and the inverse Fourier transform using the following relations, and we have proved the inverse Fourier transform. The discrete time Fourier transform can be split as a complex quantity, and it can be split into a real part and an imaginary part, and you can also combine the real and imaginary parts to get the magnitude spectrum as well as the phase spectrum. So one of the key things to note in this particular section on formulae is the limits that we have. So when you look at the limits of n, it goes from minus infinity to infinity. So basically it's it can be an infinitely long sequence for which we are computing the discrete time Fourier transform. On the other hand, the inverse Fourier transform goes from minus pi to pi. And we also made a mention that xe of j omega is a continuous function of omega, that is a continuous function of omega. Okay, that is the discrete time Fourier transform. It also is a periodic function of omega. And the reason it is periodic, because omega itself is periodic. Omega is the discrete time frequency is periodic with a period equal to 2 pi. So, but let us verify that. So, for example, if you take the expression for xe of j omega and then shift omega by a multiple of 2 pi, omega plus 2 pi k. Okay, so that is that's the expression that we have. Maybe I'll just do the brackets in a different color so you will know where the brackets are. Omega plus 2 pi k. So basically I am looking at the value of the discrete time Fourier transform where omega has been shifted by a multiple of 2 pi k. So write down the expression for the discrete time Fourier transform, summation n equal to minus infinity to infinity x of n e power minus j, and this is where omega will get shifted by a multiple of 2 pi, omega plus 2 pi k times n. Okay, and one more step, just a simple step, and you will see the answer. So this is summation n equal to minus infinity to infinity x of n. I am going to expand the term e power minus j omega n as the first term. The second term is e power minus j 2 pi k n. Okay, any exponent e power j 2 pi k n is cosine 2 pi k n plus j sine 2 pi k n, which is equal to 1. So this is equal to 1 for all k. Okay, so which means that what you are left with is summation n equal to minus infinity to infinity x of n e power minus j omega n, which is the same as x e of j omega. So x e of j omega is a continuous function. It is also complex valued. Maybe that's another thing that you can add. It is complex valued. And because it's complex valued, we can write it in terms of a real part and imaginary part. So continuous function, a continuous function of omega, complex valued function, it's also a periodic function of omega. Now, we also mentioned that this particular discrete time Fourier transform and its inverse has a very powerful interpretation. So, the another interpretation that you will find helpful is given as follows. Interpretation. Okay, the interpretation is that Fourier series representation. Fourier series you would have studied in mathematics and also in signals and systems. Fourier series is applicable anytime we have a periodic signal. Periodic signal. Okay. So, now we have xe of j omega is a periodic signal. Xe of j omega is a periodic signal with period equal to 2 pi. It is periodic in omega, not periodic in time. But Fourier series is the basic principle that as long as it is periodic, it can be represented in terms of Fourier series. So, this is a periodic signal with period equal to 2 pi. Okay. Now, that means you should be able to represent xe of j omega in terms of a Fourier series. And we can think of the discrete time Fourier transform as precisely a Fourier series representation. Xe of j omega is equal to summation n equal to minus infinity to infinity x of n e power minus j omega, complex Fourier series. And here we can interpret these x of n as the Fourier series coefficients. Okay, and typically how would you obtain the Fourier series coefficients? You would do 1 over 2 pi integral over one period minus pi to pi of the periodic signal xe of j omega e power j omega n d omega. So, basically exactly like how you would do for a continuous time Fourier series, we have been able to show that this periodic function xe of j omega can be written. So, one is the representation or interpretation of this formula as a DTFT, discrete Fourier transform pair. You can also think of it as a Fourier series representation of a periodic signal, which is xe of j omega, which is a periodic signal. It is period in omega with a period equal to 2 pi. So, I hope this gives you a good framework which helps us to link the concepts from Fourier series, Fourier transform, the continuous time, discrete time, all of them are related and we can get very good insight. So, this particular interpretation is helpful. Now, moving on. We looked at a particular example where we took a sinusoidal function cosine 4000 pi t and we looked at multiple cases where we were sampling with different sampling periods. In one case, we were sampling it with Nyquist criterion. In another case, we were sampling it with this is not satisfying Nyquist criterion. So, basically the important thing to note is that when we don't satisfy Nyquist, then what we find is that you will get a reconstructed signal which is not the same as the original signal. And by the same token, we also observed that when you did Nyquist sampling, the discrete time function was cosine 2 pi by 3. Now, cosine 2 pi by 3 can be obtained by the same input signal or by the same sampling frequency, but with different input signals. And the reason you are able to map it is because of aliasing, and what you are finding is that multiple continuous time frequencies can get mapped to the same discrete time frequency because of aliasing. So, one important thing to note is that only if Nyquist rate is satisfied, then the original signal xc of t can be obtained via reconstruction. Otherwise, what we will get is a aliased version. And the mapping from a continuous time frequency based on a sampling period to a discrete time frequency, that is not a unique mapping. You can get more than one signal which can map to the same discrete time frequency as we saw in this case. In fact, in this case, we showed that there are infinite number of continuous time frequencies which, when sampled at Ts equal to 1 over 6000, you will get the same discrete time frequency, which is cosine 2 pi by 3. something to keep in mind. So the importance of satisfying Nyquist criterion is very important, sampling criterion. Moving on. Then we saw a simple example where we looked at impulse response of a discrete time system, LTI system. We said that we can compute the discrete time Fourier transform HE of j omega, and from that we derived 3 spectra. The first one was called the magnitude spectrum, second was the phase spectrum, and the third was group delay. So keep in mind that the 3 things that you can get from HE of j omega. HE of j omega. You can get magnitude HE of j omega, that is the magnitude spectrum. Magnitude spectrum. Okay, and you can get argument of HE of j omega. We call that as phi h of omega. This is the phase spectrum. Okay, and most of the time we are computing the magnitude spectrum. Okay. Occasionally we will calculate the phase spectrum, and very rarely, but still important, we do calculate the group delay spectrum, tau h of omega, which is given by minus d by d omega phi h of omega. This is called the group delay function, group delay spectrum. So you can think of it as 3 things that you can derive from the discrete time Fourier transform HE of j omega. So from the impulse response, you get the discrete time Fourier transform. You can look at its magnitude, its phase, you can look at its group delay, and very often it is helpful for us to guess what is the nature of the discrete time system. So what we do is we check what is the behavior at omega equal to 0. We check what is the behavior at omega equal to pi, and then we all sometimes may check omega equal to. So typical frequencies that you check, typical, okay, omega equal to 0, that corresponds to the DC value or the low frequency, omega equal to pi, that is the highest frequency component that you have, that is the highest frequency. Omega equal to 0 being the lowest frequency. Okay, and there is a intermediate frequency which you can check, which is omega equal to pi by 2. That is a medium frequency, low, medium, high. And by looking at these responses, you can then tell what is the nature of the LTI system, and that is one of the powerful tools that we have with the discrete time Fourier transform. And then after that, we looked at a type of signal which is a decaying exponential, a power n u of n. This is a very, very commonly encountered signal. We looked at its Fourier transform, discrete time Fourier transform, looked at its value at omega equal to 0 and omega equal to pi, and said that it looks like a low pass filter because it's boosting low frequencies and attenuating high frequencies. Similarly, we saw multiple sequences which seem related, but you must be careful to apply the discrete time Fourier transform carefully, look at whether it is converging, and then obtain the interpretation correctly. One useful sequence is the case 4, where you have a power mod n. Mod n means it is a sequence that it basically is going on both sides, but because mod a is less than 1, it is a double exponentially decaying function on both sides, on the positive side and on the negative n side. So we can split it as a causal sequence, anti-causal sequence. We looked at its Fourier transform, discrete time Fourier transform, and then came to the conclusion that this is also a low pass filter based on that. So what I want you to take away from it is the discrete time Fourier transform is a powerful tool. It is something that you can look at the behavior of the discrete time system and understand, what is the magnitude response, phase response, is it a low pass filter, high pass filter. So a lot of very interesting and useful results that you can obtain. And we spent quite a bit of time during the last session on proving the symmetry properties, and I asked you to check on a few. I hope you've been able to do that and also review all the material that we have been looking at. There are 3 basic results that I would like you to keep in mind whenever trying to work with the symmetry properties, and here are the 3 results. Okay, the first one, always start with the underlying definition. x of n has got a discrete time Fourier transform xe of j omega, which is given by summation n equal to minus infinity to infinity x of n e power minus j omega n. Okay. The first step that we do is the step of conjugation. So when you conjugate the left hand side, you must conjugate the right hand side. And since x of n can be complex, you have to conjugate x of n, and e power j omega n is also a complex quantity. So it was e power minus j omega n, it became e power plus j omega n. And the second step is you can replace omega with minus omega, and you get once again the right hand side starts to look like a discrete time Fourier transform, a sequence e power minus j omega n. So this is how we do. So you can take the original expression, do a conjugation. You can then replace omega with minus omega. Now, after you have done that, instead of replacing omega with minus omega, you can replace n with minus m. So what happens then? Then that is a third type of modification that you can do. So if you do that, then m goes from so I think there is a mistake in this one. These should be n. This should be n equal to minus infinity to infinity. This should also be n equal to minus infinity to infinity. And when you replace it with n equal to minus n, then m goes from minus infinity to infinity. You can then you can do the substitution, and then you can get the correct expression. Okay, so these are the two things: conjugation, replace omega with minus omega, and m with minus n, and this is what will give you the t, and always coming back to the basic results. So this is what helps us in almost all of the symmetry properties that we have derived, and I hope you have had an opportunity to work with that and to study this in depth. So we will again look at a few examples. There will be some practice problems in the assignment, and also some during the interactive session. We will give you some additional things to try out.